I welcome you again for this course on earthquake resistant design of foundations for NPTEL certification. As we discussed in the last lecture that we are discussing cello foundations, and within the cello foundation the last part of that is on dynamic analysis. For dynamic analysis we have already so far 3 lectures. In first 2 lectures we talk about pseudo static analysis, where a new method was discussed and we find out the bearing capacity as well as settlement. Then we discuss a new method for where a design procedure is discussed and design example is discussed. The third one on dynamic bearing capacity we have discussed when the vertical load is applied in the transient vertical load is applied, and 2 approaches were discussed. One was Trandafilidis, another was Wallace. In the Trandafilidis it was the rotational mode of failure, while in case of the Wallace it was transient mode of failure. The Trandafilidis was applicable for saturated cohesive soils, the Wallace was applicable for C5 soil. Today we are going to talk first the case when the horizontal load is applied, because that is most important in the during the earthquakes, and when the horizontal load is applied, what will happen to your foundation, whether your foundation is safe or not, that is our objective. So, in the Tumor have did, and the Tumor's analysis is also applicable for C5 soil, which is a general soil, that is good. And then so Tumor in 1965 presented a solution for dynamic response of a strip footing which is supported by C5 soil and subjected to horizontal transient load. And you can see that the footing is here. So, in this case when we see the footing, so you could see that this footing is on the surface, that means no embedment has been considered in this analysis. And what are the assumptions? The failure of the footing occurs with the application of horizontal dynamic load acting at a certain height above the base of the footing. So, this is important and which can be easily seen in the figure shown in the next slide. So, what is issue here, that normally vertical load is always acting on there. So, Q is acting as usual, but we consider in addition to Q a horizontal load which is given by lambda Q, and this horizontal load is acting at a height h above the base of the footing, where capital H is the height of this from the base of the footing. So, this is in addition to the value of Q considered in this analysis. Then resulting moment of the footing is of a rotary nature. The failure surface is a logarithmic spiral with its center at the on the base corner of the footing, which is also the center of rotation. So, what is the where the center of rotation as well as the so what you have this point O, right. Point O is the edge of the footing, and this point O, this will be the you have a logarithmic spiral, and this logarithmic spiral is given by r equal to r naught e theta tan phi. Okay. So, what you have then this logarithmic spiral, what you have this you know the value of C, what is C here? C is cohesion and phi is angle of internal friction. So, this will be applicable, this will provide a resisting force. So, let me explain to you again that what you have here, you have from here to here, this is logarithmic spiral, and the equation of logarithmic spiral is given by r naught. What is r naught here? R naught is nothing but the width of the footing B. So, the radius of this logarithmic spiral is same as the width of the footings. So, value of r naught is already known. As value of theta changes as shown in this figure, naturally the small r will be changing, and you can find the value of r using this. So, in this figure I think everything is explained except x bar and delta x, which we will discuss later. Now, this was the second assumption, the failure surface is logarithmic spiral with the center on the base corner of the footing, which is also the center of rotation. Third assumption, the rotating soil mass is considered to be a rigid body rotating about a fixed axis. So, fixed axis which we have already discussed, that this is the center of rotation is already fixed, and this will be treated as rigid body motion. The soil exhibits rigid plastic stress strain characteristics which is the case for all the 3 theories. So, all the 3 theories which we have discussed so far assume that stress resistant characteristics is perfectly plastic. Okay. Under with these assumptions we go for the Tumor solution. So, in the Tumor solution, first of all, because you are considering a footing on the surface, so there will be no surcharge. So, the ultimate bearing capacity is given by the equation number 1, C n c plus 0.5 gamma b n gamma. So, in this equation the second term, which is q n q or gamma d f n q, is absent because there is no depth of footing, d f is 0 basically. So, C is cohesion unit weight and B is width of the footing. So, this is not a new equation. Now, continue with this. So, what we do in this Tumor solution, they have considered in all these solutions, you know that our objective is, ultimate objective is to have this displacement or rotation, and for finding that displacement or rotation, what we do? We prepare a equation of motion and solve the equation of motion and get the answer. So, here to prepare the equation of motion, you need to consider the moment equilibrium. So, we consider the moments acting on one direction equal to the acting in another direction, equate these two moments and then frame the equation of motion. So, considering moment of the forces about point O, that which is the center of rotation, the moment due to cohesion which will provide a resisting moment is given by this relation MRC CB square 210 phi, and then you have this. So, what you could see here, that besides C and B, this is a function of phi only, and psi, this notation can be simply like here is equal to what you have this term which is later on shown here. Okay, yeah. So, this notation will be equal to in the next slide it has been shown, and then similarly you have in this case also MRW, where xi is a function of these, both are function of phi only. So, we can one can be calculated. Now, what you have moment of q u about point O is will be q u b square by 2, and this will be simply MRC plus MRW. So, if we equate both the sides, then what you will get q u you will get from this equation, but if we see compare this equation with equation number 1, which is C n c plus half 0.5 gamma b n gamma, then you can get the value of n c and n gamma. So, in this case n c is coming here and n gamma is given by this relation, and you can see that both are functions of phi. So, you can consider that Tumor have suggested that n c and n gamma should be find out from these relations, which both relations are functions of phi. Okay. Now, we continue with this other moments which are acting. So, first of all, once n c and n gamma is known to you, then you can calculate the value of load which is can be applicable. So, it will be like the load, the factor with the factor of safety F, the static vertical force on the foundation Q is nothing but B multiplied by C n c plus 0.5 gamma B n gamma divided by factor of safety F, and Q is known. Then the issue is this one, what is the horizontal load? The value of the horizontal load, which is let us say Q d max, will be simply lambda into Q, where lambda is overload factor, and the value of lambda will be this, naturally this will be dimensionless. So, that you can have this. So, the Q d max is the maximum value of horizontal transient load per unit length acting at a height h above the base of the footing. Then moment due to vertical force Q is simply m1.5 into Qb, and the moment due to horizontal force Qd at any time t. Actually, this can be written as simply that Q into B by 2. So, this will be the case here, and the moment due to horizontal force Qd at any time t is given into Qd into h, where you put the value of Qd is equal to Qd max, because here how you can have this is this slide, this is something wrong here, this should be Qd max, actually this I forget to change it. So, this should be Qd max, and once you have the Qd max here, so you can have this should be Q. So, Q can be simply here Qd, or let us say Qd will be Qd max into T by Td. So, when t equal to 0, this will be 0, when t equal to Td, this will get the maximum value. So, with this you have, and this equation m2 is framed. Now, the next is moment due to vertical force q is simply this is the due to the vertical force, and then this is moment due to the basically the you can say due to the weight W. So, this is weight W, and for this check the figure here. So, what you have this here, see W always act in the downward direction, and at any point then this is the displacement, additional displacement, and this will be W into delta this you have this delta x bar. So, this is additional moment coming due to the displacement of this this here. So, what you have when W is given from this relation and delta x bar is calculated from this relation. Now, with the manipulation you can find the value of delta x bar, which is simply can be said as z bar into alpha, where alpha r and or r can be calculated from these relations, x bar is given from this, z bar is given from this relation. So, ultimately we end up in this equation where m3 is given by from this relation, where beta is given. So, all these are these moments are there. Now, the next moment is the due to the inertia force of the soil waves, which can be d square alpha dt square into j. What is alpha here? Alpha is nothing but the rotation, and let us see what is alpha. Alpha is you can see in this figure. So, what normal case, let us say you have the footing here. Now, what will happen that when you get rotate, so this alpha is an angle between you have this between C1 and C2 two positions, and so this position first position is when it is x bar, and C2 will take you to delta x bar, and this angle is alpha and this complete angle is eta. So, our ultimate objective is to get the value of alpha, which is our unknown, which is the rotation of the center of this footing, center of rotation O. So, our objective is in this case is to get the value of alpha. What is the, and naturally as a designer we will be interested in the maximum value of alpha, that is alpha max. So, what has been done here, that you have this is second derivative of alpha with the time, and m4 is given from this relation where mu c is here. So, ultimately moment equilibrium equation is framed where m1 plus m2 equal to mrc plus mrw plus m3 plus m4. So, one side what you have this left hand side the driving moments, on the right hand side you have the resisting moments. So, substituting all the values you end up in this equation, which is your equation of motion. So, your equation of motion for the Tumor solution is written here in this box. And what is k here? K is g beta sin eta mu c b, and k is a factor which is opposite of the second. So, per second will be this unit. Then you have A is given from this relation, E is given here. So, all these things are known. Now, this is the equation of motion in the moment form. We solve this equation of motion and find the value of alpha and ultimately alpha max. So, the solutions are done here. The solution of the differential equation motion with proper boundary conditions yields the following results, which has been shown. When time t is less than Td, then alpha is given from this relation. When t is more than Td, then alpha is given from this relation, and in this relation G1 and G2 in the second equation, G1 and G2 are given from these relations. One important point which I want to mention you here, that see in the first equation you have kt, t, and t is time t, and Td is the maximum value of t. Okay. So, you have this variable is t here. So, when t varies alpha will change, Td is constant. So, you have variable here, here two places, and here also, okay, m d max and t time multiplied by t here. So, three places t is coming, and in the second equation you get t here with cos kt, then sin kt, but other places you have Td only. So, this when the time t you put in these equations you can get the value of alpha. So, this is the solution, but what Tumors have done, Tumor have did find out the basically they have suggested this this value of the alpha max also, which we will discuss in one of the numerical example, that how to calculate the value of maximum value of alpha max using this numerical example. So, all the 3 theories are over now. We have discussed Trendafilidis, Wallace and Tumor. Now, I am going to discuss some of the numerical examples, one examples from each of the theory, which will make the things very clear. Let us take up the first one. Trendafilidis is the solution. The problem written is given here. A 1.5 meter wide strip foundation is subjected to vertical transient stress pulse, which can be given as QD 650 E minus 10 T. From this given function, you can make that the value of this 650 is given Q naught, and then you have then beta decaying function. Beta is nothing but 10 here, 10 second inverse, which is written here also. And the soil supporting the foundation is saturated clay with Cu equal to 60 kilonewton per meter square. The unit weight of the soil is 19 kilonewton per meter cube. Determine the maximum angular rotation of the footing which it might undergo. So, how we do it? Qu is given by 5.54 Cu. Cu is given, so we get the value of Qu here. Now, because this lambda is nothing but Q naught over Qd, Qu, and Q naught is given you 650 and 332.4. So, you get 1.955, which is the load factor. Beta values is already given. Now, what we do for these values of lambda and beta, from the chart which has been given by the Trendafilidis, we find the value of this factor, but that chart should be used for b equal to 1.5 meter. So, we will use the chart for 1.5 meter, and putting the value of lambda 1.955 and beta 10, we get this factor. So, the chart is given in the next slide. This is not very clear, but this is for b equal to 1.5 meter, and beta is given you 10 second. So, beta 10 seconds. So, you have this line, that means the second last line. So, this curve will be selected. Then overload factor is about 2, and for this value you get roughly this you get here somewhere, and so where you end up here. So, you get this value between 10 to power minus 2 to 10 to power minus 3. So, this value comes out to be 0.00298 from this chart. So, this value is picked up from that chart, and now what we do here, W is known to us, W is 0.31 gamma b square. So, this is calculated 41.61 kilonewton, and the substitute the value of W in this equation, and then you get 0.158 radian, that is 9.1 degree. Okay. So, this is how it is done, you find out. Continue with this second example, which is for the vertical case, but this load is applied in the reciprocating mode, and there is a footing with a width 2.5 meter and depth 1.5 meter, that means b equal to 2.5 and df equal to 1.5 meter. So, what is done for this case, that we have the equation of motion, we have this is for Tarjagi's theory, which gives the ultimate bearing capacity C n c plus gamma df n q plus 0.5 gamma b n gamma. So, all the parameters which is given here C phi, and then you have this gamma, we set up this equation which is given here 50 n c plus 27 n q plus 22.5 n gamma. Here the n c, n q, n n gamma need to be find out, which has been given by this researcher, that is Wallace. So, this is given in this case. So, you could see here what we do, we calculate the value of Qu for different value of values of k, and in this table you can see that the minimum value of Qu is when k equal to 0.15. So, the k we select is 0.15, and for this case you get Nr from this table as 10.0081. So, in the next slide what you have, the minimum value of Q is obtained as 2204 kilonewton per meter square, which is at k equal to 0.15, and for this value of k and phi equal to 30 from the table, you get Nr equal to 10.0081, and the ratio Nr by Ni is 5.83033, which is also coming from the last table. Then we find this factor nr gamma q putting this. So, all this comes. So, ultimately we get the value of k prime which is 2 nr nib from this equation, and you get the 5.22 second inverse square, and the ratio of qd max or qu comes of 1.36 which is your load factor. So, then TDK prime is calculated as 1.566. Now, for this given data, for this ratio of 1.36 and TDK 1.556, we can find the value of delta max, and for this delta max we need to use the chart which is given by this Wallace. So, this chart, what we do here, this ratio is 1.36. So, you need to select the curve for 1.36, that means roughly this curve will be this curve, and the value of this factor TDK, this factor TDK is 1.566. So, what you have 1.566. So, you select 1.566, and from this chart you get the value, if you have here 1.566 will be somewhere here, and then you get this curve. So, you pick up from this chart some value, and this value comes out from this is ratio comes out is 0.034. Okay. So, 0.034 you read from this ratio. Now, this ratio itself is gamma nr q delta max. So, we put the value back and calculate the value of delta max. So, delta max you ultimately get is 0.416 meter, which is your answer. So, this was the second example on dynamic analysis, which is basically on Wallace solution. The third one, which is based on Tumor solution is third example. In this case, the load applied is the earthquake load applied is horizontal. Of course, the vertical load will be always acting, but in addition to you have a transient horizontal load in this case, and the data given is again B for the footing is given 2.5 meter, and depth of the footing in this case will be 0 because it is considered surface footing. So, continuous surface footing subjected to load, the duration is given 0.4 second, that means TD is given 0.4 second. Okay. Then applied at a height of 4 meter, capital H is 4 meter. Then from the base of the footing the properties are given, gamma, c and phi is given. So, and then finally also compute the rotation at time t equal to 0.6 second. So, let us first work on this when the t equal to TD, what happens. So, what we do in this case, first find the value of q using a suitable factor of safety 2. So, how you can find NC and N gamma, because it is a surface footing. So, you do not require, there is no surcharge. So, NQ is not required. So, NC and N gamma is calculated for phi equal to 32 degree. Phi is given to you 32 degree. For this value of 32 degree we find NC and N gamma, and this is coming 79.4 and 200. And then we find using Q using Tarjagi solution, only the difference here, this is that we multiply by B for ultimate bearing capacity, then divide the factor of safety, and then get factor of safety is 2 here. So, you get a load 8290 kilonewton here. Then other parameters which is given in this theory Tumor, this psi, then epsilon, and then you have this mu c, beta and eta, they are calculated here. So, this is this value, and then you can see that all these equations are there. So, what do we need to do? One thing which is common, that all these parameters are depending only on one parameter which is phi. So, you could see phi is coming. So, once phi is known, then you can find 1, 2, 3, 4 parameters, and then the next one after this calculating this parameters, once you have these parameters, then we also find the value of x bar and z bar. Now, x bar is also a function of phi, but in addition to phi it is also depend on b. So, in terms of b you find x bar which is minus 2.52 b and then 2.85 b, and finally sin eta can be calculated as a ratio which comes out to be 0.75. Okay. Then we continue to find other parameters k, a and e, which is calculated in this equation. K is calculated here, a is calculated like this, and then e is also calculated like this. Once all these are calculated, then in the next step, the value of maximum moment which is h into qd max, where qd max is nothing but lambda into q. Q is known to us, but lambda is not known to us, height is also known. So, ultimately md max is in terms of lambda. Now, lambda is unknown here, and the value of lambda which gives you the value of alpha equal to 0 will be called lambda CR, that is critical value of lambda, where alpha will be 0. So, what we can do for given value of t equal to Td at t equal to Td at 0.4 second, find that value of lambda which you will give you the value, that is the load factor where you do not get any rotation. So, alpha is given this relation, we put all the numbers here and then equate alpha equal to 0. So, what you get? You get an equation in alpha in terms of lambda and then equate this equal to 0, then ultimately you end up in lambda equal to 0.948, which is lambda CR. So, this is your first answer. That means, the load factor should be 0.948 to get the 0 rotation. And then now the next part of the question is asked is that, so first part, determine the value of maximum horizontal load that can be applied on the footing. So, maximum horizontal force that can be applied is lambda into q, where lambda is already find out. Now, for this load, find the rotation at time t equal to 0.6 second. So, for 0.26 second, we need to use the equation which is for the second part of the equation, when this equation will be applicable when t is greater than Td. Okay. So, when t is greater than Td, then you use this equation, and in this equation we put all the numbers, and all the numbers has been put up, and ultimately you get 0.8229 radian. So, this gives you the value of t. So, and this was the last example here. So, all these examples and theory has been detailed out in these two references, a book by Professor Prakash and another book by Professor Swamisaran, and all that has been further detail can also be found out there. And with this I complete this today's lecture here, and not only we have completed dynamic analysis for shallow foundations, but with this today's lecture we have completed all the portion of the shallow foundations. So, I thank you very much, and the next lecture we are going to talk about the next module. So, let me go through this what is like our modules, where we are and what we will be covering in the next lecture. So, let me just have a brief about that. So, our module introduction is over, shallow foundation is over. So, we will discussing third one, pile foundations, okay, and pile foundation is a big topic and very important for earthquake loading. So, we are going to start in the next lecture. Thank you very much for your attention.